Hello, everyone, and welcome to What's the Story, Gemini, the podcast where I ask Google Gemini about a topic and then we learn about it together. Today, I decided to ask Google Gemini about thermodynamics. Don't ask me why, actually, you probably should ask me why. I have found myself recently going down a rabbit hole within YouTube about biology, about the theory of evolution, and basically theory of evolution versus the theory of creationism. And although I am not going to get into those two subjects, thermodynamics does come up a lot. And because I wanted to make sure that the narratives I am hearing on these particular channels, I'm actually understanding better, and they are not telling me falsehoods, I figured, hey, let's learn about thermodynamics, because I never learned about it back in college. I knew a lot of my friends, they were engineers, and they did thermodynamics. And yes, I myself was also an engineer, but I did biomedical textiles, and I'm not that type of engineer. We learned about braiding and weaving and knitting and how all of those particular materials interact with the body and so on and so forth. So, like I said, not that type of engineer, so I didn't do thermodynamics. So, let's learn about it together today. Thermodynamics, a fundamental exploration. Thermodynamics, the study of energy and its transformations, is a cornerstone of physics and chemistry. It provides a framework for understanding a wide range of natural phenomena, from the behavior of gases to the evolution of the universe. I'm really sorry. I am 5. I'm cracking up. Okay, by the behavior of gases. Okay. If you don't understand why I'm laughing, I'm not going to explain it to you because I'm a little ashamed at how much this is making me giggle. So just give me a second to collect myself and I'll continue. This paper will delve into the fundamental concepts of thermodynamics, exploring its laws, key terms, and applications. The laws of thermodynamics. The laws of thermodynamics are fundamental principles that govern the behavior of energy. There are 4 primary laws. So I'm actually going to interrupt on this, and I know we haven't gotten far into this. This is the first time I've heard that it's the behavior of energy. I have no idea why. Whenever I hear, thermodynamics, I hear of the law of thermodynamics that, like, matter cannot be created or destroyed, which I think is part of thermodynamics. But this is the first I've seen it's actually energy. And I'm sure everybody who studied thermodynamics is yelling at me, like, no shit, Sherlock. But as I mentioned, I'm not that type of engineer, and I did not learn this stuff in school. The 0th law of thermodynamics. I think I'm saying that right. This law establishes the concept of thermal equilibrium. It states that if 2 systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. This law provides a foundation for defining temperature. The first law of thermodynamics. This law, also known as the law of conservation of energy, states that energy cannot be created or destroyed, only transferred or transformed from one form to another. It establishes the concept of internal energy, which is the total energy of a system, including kinetic and potential energy. The second law of thermodynamics. This law introduces the concept of entropy, a measurement of the disorder or randomness of a system. I think this might be about myself. It states that the entropy of an isolated system always increases over time or remains constant. This law sets limits on the efficiency of energy conversion processes. The third law of thermodynamics. This law deals with the behavior of matter at absolute 0 or 0 Kelvin. It states that as the temperature of a system approaches absolute 0, its entropy approaches a constant value. Heat and temperature. Heat and temperature are related but distinct concepts. Temperature is a measure of the average kinetic energy of the particles in a system. It is a property of matter that determines the direction of heat flow. Heat, on the other hand, is a form of energy that is transferred between systems due to a temperature difference. Okay, so this is kind of like every parallelogram is a square, but not every square is a. Hold on. This is kind of like every square is a parallelogram, but not every parallelogram is a square. I think. Systems and surroundings. A thermodynamic system is a region of matter or a collection of objects that is being studied. It is isolated from its surroundings by a boundary. Systems can be classified as open systems. These systems can exchange both matter and energy with their surroundings. Closed systems. These systems can exchange energy with their surroundings but not matter. Isolated systems. These systems cannot exchange either matter or energy with their surroundings. Thermodynamic processes are changes that occur within a system, such as heating, cooling, or expansion. They can be classified as reversible or irreversible, depending on whether the system can return to its original state without leaving any changes in its surroundings. Energy and work. Internal energy is the total energy of a system, including the kinetic and potential energies of its particles. It can be changed through heat transfer or work done on or by the system. Work in thermodynamics is the transfer of energy between a system and its surroundings due to a force acting over a distance. It can be mechanical, electrical, or other forms. Heat transfer. Heat is the transfer of energy between systems due to a temperature difference. Here we are for little parallelograms and our squares again. There are three primary modes of heat transfer. Conduction, the transfer of heat through a material without the movement of the material itself. Convection, the transfer of heat through the movement of a fluid. And radiation, the transfer of heat through electromagnetic waves. I'm pretty sure this isn't actually like on topic, but because this mentioned convection, I recently got an air fryer and I'm kind of obsessed with it. So if you guys don't have air fryers, I recommend that you look into them because they are magical, like narwhal magical. And because of me being obsessed with my air fryer, my best friend essentially tells me there are three things in this world that I love. Air fryers, YouTube, and potatoes. When you eat an air fryer, you'll understand why the potatoes. Heat is measured in units of energy such as joules. Heat capacity is the amount of heat required to raise the temperature of a system by 1 degree Celsius. Specific heat is the heat capacity per unit mass. All right, already we're just like off the grid because I'm in America, and we use Fahrenheit. So I gotta learn Celsius. I feel like, I mean, Kelvin, I vaguely remember, and I know that I learned Celsius back in school, but that was a while ago. I should learn Celsius. Add that to my to-do list. Learn Celsius. Applications of thermodynamics. Thermodynamics has a wide range of applications in engineering and technology. It is used in the design and analysis of engines, refrigerators, power plants, and other energy-related systems. It is also essential for understanding the behavior of materials and chemical reactions. In the field of cosmology, thermodynamics plays a crucial role in understanding the evolution of the universe. The Big Bang Theory, which proposes that the universe began as a hot, dense state, is based on thermodynamic principles. The whole universe was in a hot, dense state then. The concept of the heat death of the universe, a hypothetical scenario where all energy is evenly distributed and no further work can be done, is also rooted in thermodynamics. Thermodynamics provides a powerful framework for understanding the fundamental laws that govern the behavior of energy. Its applications extend across a wide range of fields from engineering to cosmology. By understanding the principles of thermodynamics, we can gain a deeper appreciation for the natural world and the laws that govern it. Okay, so maybe 50% of those words I actually understood. I'm sure somebody much smarter than me could listen to this and it might sound like I'm reading C Spot Run. In which case, God bless you, you know? And anyone in STEM, especially my ladies out there, God bless you. Um, because this is not something that I do. Again, you had me at convection because it made me think of an air fryer. So if that is any indication of where I am when it comes to science, um, I'm not. I'm not there. I'm not. But for those people who understand this and they find passion about it, I I'm jealous. I'm honestly jealous because this sounds extremely fascinating. It sounds like understanding a world far outside of ourselves. And I imagine that that is a wonderful feeling to understand science because to me, science is a lot like magic. I know that's a weird way to kind of think of it, but it's just impossibly amazing what the natural world is capable of doing. And these people that work in science or make these discoveries are essentially, to me, discovering the magic that makes the world around us. So thank you. Thank you for your interest and your passion and your continued investigation into this crazy, beautiful natural world. And thank you for listening. This has been What's the Story, Gemini?